Your exam scores, as you hopefully saw, are on Moodle right now. I'm not returning the exams to you yet because there's still 1 or 2 people that need to take the exam. So the expected back here was probably Wednesday, Thursday, or Friday of this week. The scores were a little bit lower than the first exam. I think the average on the first exam was around 86, 87, 88, and the average in this exam was more like 81 or 82. So it was a lower average, but it was actually more typical of what happens with most of my exams. The averages do tend to be more like around 80% or so. And that is just for the in-class portion. You still need to grade your take-homes. I hope I can get that done by Thursday or so this week. I'm going to give a little talk on Wednesday. I forgot to mention to the previous section, so I'll probably send you a note about it as well. But I'm going to be giving a little talk on Wednesday about some things I learned at the Wolfram Technology Conference, giving a presentation on Mathematica. The time and day are set at Wednesday at 3 to 4 o'clock. The location has not been set. I'm guessing it's probably going to be CC 230 or CC 325. But I think what I'll do is I'll have anybody who's interested just send me a note saying that you'd like to come. That would be the way of expressing interest, and that'll help us decide which room to pick. But probably it's going to be one of those 2 rooms. I'll try to remind you of that with an announcement on Moodle sometime later today. All right, we need to spend a good chunk of time talking about the project here and showing you a few more things. Perhaps around 25 minutes or so talking about the project before we get into the content of chapter 14. So, what do I want to say? Well, first of all, what you should be working on to this point, and certainly this week if you haven't started yet, is you should be working on giving a good explanation of the differential equations, how to derive the differential equations, to describe our situation that we talked about for the project, where you've got the Earth stationary at the origin. That's an assumption we're going to make. To keep things as simple as possible, we're going to assume the Earth is stationary at the origin. That's the first simplifying assumption you're going to make. We've got the moon and the spaceship in here too. And even though they are in there at certain locations with certain velocities, you're going to assume, to simplify things, that the Earth is unaffected by the masses of the moon and the spaceship. Earth is unaffected by the masses of the moon and or the spaceship. Okay? Is that true? Not technically. Technically, it is affected, especially by the moon. But it's a simplifying assumption that we're going to make that helps the differential equations be simpler. It's not as accurate as assuming the Earth is affected, especially by the moon, but it keeps things simpler, and that's what we want to go for here, is simple. What else? We've got the moon. The moon is only affected, according to Newton's laws, by the mass of the Earth, not by the spaceship. Okay, the moon is only affected by the mass of the Earth. Finally, the spaceship is affected by both the mass of the Earth and the moon. So those are assumptions that everybody needs to make. And then the main thing you're trying to do is explain, as best you can, and in your own words, I will check for plagiarism, how to derive using Newton's laws, how to derive the differential equations that describe what's going on here. And we talked about that in class, and I've got Mathematica code that we saw, that we used to model that. It was in the section labeled with celestial mechanics. Here were the differential equations in vector form and in scalar form. I'll let you look those over. And here was some Mathematica code that can simulate what's going on. You can essentially use this Mathematica code. You're trying to explain it first, and you can use it. If you run this particular set of code right here, this is the output, an animation showing the Earth at the center there, at the origin. The moon is following the black trajectory, and the spaceship is following the red one, and you can see the gravitational effect of the moon on the spaceship is causing the path of the spaceship to bend a little bit. You're probably going to want to go further than that, though. You're going to want to use this kind of code, which is a bit more general. Oh, I forgot to clear some things. Let me just go ahead and quit the kernel. I think if I cleared some of these variables ahead of time, then we wouldn't get that message. But once you quit the kernel, now you can show the graph of this. And I've added more manipulate sliders to not only show time going by, and I also made the moon in gray there as a dot, but also allow me to change the initial position and the initial velocity of the spaceship. And if you experiment with these, you can get some pretty interesting behaviors. So for example, look at this one. The spaceship is being affected greatly by the gravity of the moon. And if we run time further, maybe it's going to go out that way. I think we can even get it to bend toward the Earth. We go far enough. Yeah, there we go. Isn't that cool? So there we have an illustration of the slingshot effect. The spaceship is heading toward the moon, and it comes close enough that it has a great effect on its trajectory, and it goes back around the Earth. If I move time backwards here, this top slider, we'll see that the moon and the spaceship come pretty close together. Do they touch each other? Does it crash? Well, no, not in the mathematical model, because you're treating them as points. So even though I've got big blue and gray dots there for the moon and the Earth, the math is treating them as points, and they're not going to touch as points. Okay? Even though in real life, theoretically, they could crash into each other. Okay, so you can experiment with different things here. But what are you going to want to do if you want to get a good grade? So what I've told you so far, using these assumptions, explaining how to derive the differential equations, that's the main part of the content that you do. And then you use the code to illustrate what's going on. If you do a really good job of that, that might get you close to 90% of the project. But if you want to get higher, if you want to get close to 100%, I'm going to want you to go further than that. And there's various kinds of ways you can try to go further. You could try to see if you can't get the spaceship to go into orbit around the moon. If you do, it's a little extra tricky. You need to use NDSolve in a piecewise way in order to get it to go into orbit around the moon. Essentially, you're going to want to imagine that you change the velocity vector of the spaceship instantaneously. Now, that can't happen in real life. At this point, maybe the velocity vector of the spaceship looks like this. You can't change a velocity vector instantaneously, but for the purposes of this project, it's a simplifying assumption you can make as well. Probably you're going to want to try to make the velocity vector a lot shorter at a certain instant in time to try to get it to go into orbit. But if you're going to do that, you're going to have to use NDSolve in a piecewise way. Let's do an example, a simpler example, to illustrate how to use NDSolve in a piecewise way. So I'm about to write down a real simple differential equation. There's a pretty simple differential equation. To solve this equation, you're looking for a function, x is a function of time, where the derivative of the function is the the opposite of the function for all values of time. You don't see a t over there, but that's the implicit assumption that x is a function of time here. Let's add an initial condition. Let's say x of 0 equals 1. That's called an initial value problem. It's pretty easy to solve. Does anybody think they know? Just by looking at it. Find a function whose derivative is the opposite of the function for all t and goes to the point 0, 1. Should be able to guess the answer. What? It's a guess, not quite right. E to the negative t does it, yeah. There's a function whose derivative, because of the chain rule, is the opposite of itself for all t. Here I am making the t explicit right there. I wrote x of t. Here I'm not. It's more traditional when you write differential equations to not make the t explicit on the right side there. There's some good reasons for that, actually. Here I am making it explicit. The derivative of this function always is the opposite of itself. So it solves this differential equation. It also solves the initial condition. X of 0 is e to the negative 0, which is e to the 0, which is 1. Okay? Once I made a mistake in the grad school exam. It was a really, really bad mistake. I accidentally wrote e to the 0, 0, 1. I'm going to erase that. Pretend you never saw that. Okay? My professor, he talked funny. He talked like this, and he whenever I made mistakes, especially if they were stupid mistakes on the test, he'd write crazy comments and he'd say, "What? Were you sleeping? Are you crazy?" He'd write things like that when I made stupid mistakes. He was a great professor, though. Actually, I really liked him a lot. Good teacher. Anyway, never make that mistake. This is one. It solves this initial value problem. Let's check that in a couple ways in Mathematica here. First of all, that differential equation is simple enough that I can use DSolve instead of NDSolve. DSolve is going to solve the equation symbolically. It's going to find a formula for the answer. Notice that when I type the differential equation into Mathematica, I do need to make the t explicit on the right side. I told you that before. Here's the initial condition, x of 0 equals 1. Put those things inside a list separated by a comma, like this. You're going to solve for x as a function of t. Okay, yeah, that's okay. If you put an x of t in here like that, then it looks nicer. There we go. X is equal to e to the negative t. Okay, so this is definitely the best way to go with this particular example. NDSolve can be used as well. Here. Actually, NDSolve works better if you don't put a t right here. And you do need to give a range of values for t, starting with the initial value of 0 in a list like this. Let's go to time equals 3. So when you enter this, it does not produce a formula. It produces something kind of strange. It says interpolating function, gives you a graph. Actually, before version 10, it did not give the graph. So this is kind of a nice add-on to version 10, as we see the graph there too. So this plus symbol, we could see more here. Order 3, Hermite false. Okay, that's probably talking about the method of interpolation, is my guess. I don't know for sure what's going on internally with NDSolve. My guess is it's producing some data, some points, and it's connecting the dots with an interpolating function. That's what the interpolating functions do, is they connect dots in this kind of situation, at least. According to some method, some Hermite method is probably what's going on. We need to be able to access that data in some way, and if you look at the documentation center, they often do that. If you look up NDSolve, they often do that through the use of a command called evaluate and a /dot. Just Mathematica's way of accessing that information. So we mimic what they do. They give this output a name typically. I call it solution. So now this is stored in that variable. Whatever's going on here with the points from the interpolating function. Now I need to access that data somehow. With a regular plot, I can do evaluate x of t slash dot solution. It's just Mathematica's way of accessing that information. Don't worry about the details of why it works. I don't know that myself. T goes from, say, 0 to 3. There's a plot of the solution. That does look like a graph of e to the negative t. In fact, you could even plot the graph of e to the negative t here as well. And we'd see that this solution, this approximate solution, is so good that these graphs are going to look like they're on top of each other. In fact, if I color the first one red and the second one blue, they combine to make purple. Or they did in the last class. Okay. I guess it does look purple on the screen. It doesn't look purple on my screen. I know what I can do to make this more explicit. I can add in some extra thickness here. Let's make the red one extra thick. This 0 to red. And we'll make the blue one less thick. Thickness 0.01. Okay, they are on top of each other. So the numerical approximation from NDSolve is producing a graph that's indistinguishable from the graph of e to the negative t. Okay? It's not using a formula to do it. It's using numerical data and interpolating functions. But how do you use NDSolve in a piecewise way? That's what you're going to need to do if you're going to want to change the velocity of the spaceship at a certain instant in time. Okay, again, that's not what really happens in real life. It can't change instantaneously. But for the sake of keeping this as simple as possible, we'll assume you can do that. How could I use a piecewise approach in this case? What I'm about to do next is a little strange. I'm going to type x approx of t. I'm going to define a function I'm calling x approx to be essentially this thing that you see right here, where you access the data from NDSolve with evaluate and the slash dot. If I do this, if I enter that, then I can, I believe, replace this with x approx of t and get the same graph. Yep. I can also evaluate x approx of t at specific values of t, like t equals 2. 0.135325, ignore the curly braces. Not quite sure what the root of those, but I don't think it's a big deal. Is that right? Is the approximation at time 2 about 0.135? There's t equals 2. Looks about right. Let's change, let's imagine, if this were a motion or something, imagine hitting it with a hammer at time 2 so that the motion goes up here. Let's change the initial condition at time 2 to be something different. In fact, let me go ahead and call this thing solution 1. Change this to a solution 1 as well. Let's do a solution 2. Change the 1 to a 2. And let's change this initial condition from being x of 0 equals 1 to x of 2 being, well, anything other than 0.135535. To make a graph that's going to be discontinuous. That's my goal. Is to make a graph that's discontinuous, that jumps at time equals 2 to something having a value other than that. Maybe I'll jump up to 1 again. So I'll keep the right-hand side here 1. That's going to produce another interpolating function. Is it possible to piece these together? That's the issue. Is it possible to piece these together? And the answer is yes. What I can do here is I can use this basic math assistant and the piecewise button that you see right there to create a piecewise defined function. Copy this first here. It's going to equal the first one related to solution 1 that came from the first application of NDSolve when t is between 0 and 2. And it'll equal the second one that comes from solution 2 when t is greater than 2. That's a piecewise formula. than 0 and 2, use solution 1. When t is bigger than 2, use solution 2. I'm putting these together into one function called x approx of t, and now if I graph that, it's got to jump just kind of quick. Each piece, this piece and this piece, those two red curves, each of those satisfies the differential equation. I'm piecing them together in a discontinuous way to create just one function, both pieces of which solve the differential equation. In fact, this one, because this one's just going to be a horizontal translation of the first one. Translate the first one over to, it should equal the second one. We can check that by doing, let's see, x approx of 1 should equal x approx of 3. It really is a horizontal translation. Yep, very cool. So it's a horizontal translation to the right by 2 units. So what I'm trying to get at here is you can use NDSolve in pieces to, for example, now with your project, piece together the solution that is going on from when the spaceship is right about here to when it's right up there, to after you change the velocity vector instantaneously, make it a lot shorter, for example, it's probably the best thing to do, to a solution that goes around the moon. Yeah. We're going to try to piece those together. You're not going to worry about the details of how that would actually be done with a rocket. Of course, if you were an engineer, you'd have to worry about those details. Like you wouldn't want your astronauts to be subject to too high of g-forces as you decelerate. It also is going to occur over a certain interval of time. It's not going to happen instantaneously. So you'd have to worry about those kinds of things if you were doing this for real life. But this is a good enough approximation for us.
What are we assuming for the initial position of the spaceship?
You can assume lots of different things. I just say close to Earth. Okay, pretend you could try to make it realistic. And by the way, now trying to make things more realistic, that's another way you can get past the 90% threshold to try to get into the A range and try to get up close to 100% of the project, is to go beyond the basic call of duty. The basic call of duty you're being using these assumptions to describe how to derive the differential equations and using Mathematica in the ways I've shown you so far. If you can get the spaceship to go in orbit, okay, in a nice way, that's definitely worth some more points. If you want to use realistic data, I think that's worth more points too. That can actually be accessed from Mathematica as well. There's a command called AstronomicalData, believe it or not, that looks up astronomical data for you. It's in the documentation center. AstronomicalData. Okay, first essentially you have to load it. Let me just copy and paste this into the regular notebook so you have it saved there. If you enter this line right here, it's going to look up some astronomical data. It doesn't do it instantaneously. Watch. It starts installing the data from the Wolfram Research Data Center. So it's installing it into your session, evidently into your kernel. And now it's, after it's initialized, it's going to be in there. What can you do with that? You can use it with Graphics 3D to make a graph of the actual orbits of the planets. I guess I can do it here. Maybe I should copy this as well. Okay, I think that includes all 8 planets. Remember, that Pluto doesn't count anymore. And evidently the scale is correct. The inner 3 planets are pretty small. Maybe you can't even see Mercury's orbit. Well, unless that smallest circle is Mercury's. And they're not centered at the same spot, because they are supposed to be ellipses of a certain eccentricity, remember. So this is correct. They're not actual circles. I believe you can look up, let's see, astronomical data. You can, for example, look up the Earth's position. How about that? Oh, wait. Did I spell something wrong? I did this in the last class, so why is this not working? Oh, maybe it needs to be a capital. There we go, okay. So it's going to look up the Earth's current position in a three-dimensional coordinate system with the sun at the origin. Look at that. In meters. Okay, there's some plane it's referring to. So the z coordinate is negative 225,000 meters below whatever plane it's referring to. X and y coordinates in meters, you know, that's what, 10 to the 10th is 10 billion, so this is 83.5 billion meters. And the 11th is 100 billion, so we got 123 billion meters. And it gets updated. Watch, if I enter this again, the numbers will change a little bit. Ready? Watch them, 1, 2, 3, go. It's updated. As time goes by, this is real time. So you could find the Earth's position, well, if you wanted to include the sun at least. Can you find the moon's position? Yes, and it should be fairly close to the Earth's. There it is. On the scale of the entire solar system, these numbers are not too far away from each other, although the moon, boy, it's about 25, 30 billion meters, or 30 million meters. That's kind of surprising. I'm not exactly sure what's going on with that one, but these other ones are, I mean, on a relative scale, that's still pretty close. So, and that should get updated too. Ready? 1, 2, 3, watch. Yep, changed a little bit. Okay? So you could use real data like that. You could also use real eccentricities if you wanted to make these orbits elliptical. To model that, I mean, how would you model that with the differential equations? Then you need more accurate initial conditions. That's what you would want to do. So I don't know if it does velocity vectors. I haven't tried this yet. Velocity. Oh, it looks like it's not doing velocity. It did come up as an option. Okay, that's too bad. So if you want to use real data like this, at a certain instant in time, okay, you can pick the instant in time you want. That would be something else you could do. Try to get more points. You could try to think about area swept out functions and distance traveled functions. Might not be clear how to do that. I'd probably have to experiment with that myself. But all these things are things you can do to try to get up toward a higher grade of closer to 100%. By the way, I'm not guaranteeing you're going to get close to 100% if you do these things, because you need to do the writing well. You need to explain how to use Newton's laws to derive the differential equations well to get a good grade. That's the main thing of grading. Can I clarify anything? Okay, I'll save this, put it on Moodle, you can see what I did. But you can also look things up in the documentation center. All right, so what time do we have here? 1:30. We've got about 20 minutes to start talking about two main goals that I have for chapters 14 and 15. Chapters, question, when is the project due? Yeah, I told you it was going to be due Monday, November 10th, I think it is. It's 2 weeks from today. That's when you're going to do that. You should really make sure you work on it this week. This Friday's assignment, again, we have no class on Wednesday. This Friday's assignment is just going to be completion-based, although it will be 2 sections worth. So you're going to want to make good progress on your explanation and experimentations project. And that's part of my point with this project, is to do some experimentation with Mathematica. You're trying to see what you can get it to do. Can you model things well with Mathematica? All right, what I want to do with chapters 14 and 15, there's a lot of content in chapters 14 and 15, probably especially chapter 14. We're looking at the main points of emphasis for Calculus 1 and Calculus 2, but now in a multivariable calculus setting. Differentiation and integration. And I want to put both of those topics in the context of a certain kind of application, though the application is a little bit fake, you might say. I'm not going to be using real data. Maybe I could find some real data about this. I'm going to be putting it in the context of density functions, both for what you might describe as thin plates of metal, maybe, and also three-dimensional solids, whether metal or not. We're going to be talking about how to take density functions and do 2 things with them. Optimize them, figure out where they are largest and where smallest and largest. And secondly, integrate them to figure out the total mass. I put the word mass in quotes because it won't necessarily always have to be a physical mass. The density might represent a population instead, and then the mass would be the total population. So it's not necessarily a mass in kilograms or something. It could be a population density and a population mass. And again, by population mass, I actually mean an actual population. But I think it's good to try to put everything in these chapters into some kind of context like this, even though formulas like this are kind of fake. All right, here's a formula for a function we're going to think about today and probably some other days here. That function is just something I made up on the spot in the last class period. Actually, I had to experiment a little bit with it to try to get it to behave the way that I wanted it to. I think I initially had just that part, but the graph wasn't super interesting, so I added on a minus 10x there to make it a little bit more interesting for the graph. And then I added on 150 there to make sure it was non-negative over a certain domain. But what we're talking about in chapters 14 and 15 here are different kinds of functions than we've dealt with so far. We're talking about functions whose domains are two-dimensional. R2 essentially can be thought of as standing for a two-dimensional plane, where the points can be described with real number coordinates. That's your domain. The domain is two-dimensional. Those are the inputs, and then typically people draw an arrow in this case to indicate that the points in this domain are getting mapped to points in what's called the codomain. The codomain is the real number system, the real line, a one-dimensional thing. The codomain is one-dimensional. And I use the word codomain, which maybe you've never heard of in a math class before. Sometimes teachers will only use the words range and image. I'm going to use the word codomain. I think it's a better word to use here. All I'm emphasizing is that the outputs are numbers, are real numbers. That's all I'm emphasizing when I write that. I'm not saying whether this function is onto, for example. If you've heard of that word before, I'm not saying that all possible real numbers are outputs. If they were, then it would be onto, if you recall what an onto function is. We're not going to really worry about that. For me, range and image are synonymous, and they're the set of all outputs, which is not what this is necessarily. You can also write it in an equation form, z equals f of xy. So again, the input is two-dimensional, 2D, and the output is one-dimensional. Output is 1D.